Hello everybody. In this video we're going to be going over week 4's lecture content. Week 4 is only going to have 3 sections. This is because these are kind of big idea sections, but also this week we're going to have the midterm, and I want you guys to focus a large portion of your energy at reviewing the content thus far, because the midterm is going to be cumulative, covering everything that we've done so far in the course. In section 5.1, we're going to define energy and distinguish between different types of energy. We're going to distinguish between the related properties of heat, thermal energy, and temperature. We'll talk about what the differences between these things are. We're going to define and distinguish specific heat and heat capacity. And then we're going to finish off by performing some of the calculations that involve heat, specific heat, and temperature change. So chemical changes and their accompanying changes in energy are important parts of our everyday world. A couple examples of this is reactions involved in the metabolism of food, the energy we get from burning fossil fuels like gasoline, natural gas, and coal, and the production of all the useful products that we have from raw materials. Thermochemistry is the study of the heat absorbed or released during chemical and physical changes. So an example of energy being released from a chemical state is lighting a match. You form a chemical reaction between the strip on the box and the phosphorus coating on the matchstick, and that produces a flame that releases a lot of heat. But there are a lot of examples out there. There's the energy that we get from eating food, the gasoline that we burn to push our cars, and the processing of coal to create iron ore, and steel. So energy is the capacity to supply heat or do work. So if any time that anything gets hot, or it absorbs heat, or it's physically moving around, it's expending energy. There are 3 types of energy that we're going to talk about at first. There's the potential energy, the energy an object has because of its relative position, composition, or condition. So you can kind of think about potential energy as the energy that an object can potentially release. A bowling ball dropped from 3 feet is going to have a lot less energy than a bowling ball dropped from the top of a skyscraper, for instance. Kinetic energy is the energy that an object possesses because of its motion. So a baseball rolling across the grass doesn't have as much energy as a fastball that's been thrown at 100 miles an hour, for instance. Chemical energy is the energy that is contained within a chemical compound that gets released, like our match example. So one way to picture potential energy is if you think about waterfalls, right? That water has a lot of energy that's released when it's dropped down, and we can actually harness that by making dams and stuff to turn turbines when it drops and produce a lot of electricity doing that. So just like we had a law of conservation of mass, there's a law of conservation of energy. That says that during a chemical or physical change, energy is not created or destroyed, it's only moved from one form to another. So thermal energy is a subset of kinetic energy, and it's associated with the random motion of atoms and molecules. Temperature is the quantitative measure of this thermal energy. And basically, if something is hot, it means it has high thermal energy and the particles are moving really fast. Whereas if it's cold, it has low thermal energy and the particles aren't moving very much. So you can kind of see that in this example where our hot liquid has particles that are vibrating quite rapidly, a lot of them moving around, whereas the cold liquid, they start to get a little bit closer together and they're not vibrating quite as much as they were before. We can measure temperature in a number of different ways. One of the classic ways is through expansion, whether that be a liquid inside of a glass that expands and rises up the glass tube, Or this guy here that's called a thermocouple. You see these a lot in like old school kind of thermostats and stuff like that. And basically what happens is as this heats, this coil will actually start to unwind. And as it cools, it'll contract down more. And by measuring the deflection across that, you can kind of tell how hot or cold it is. So heat is the transfer of thermal energy between two bodies at different temperatures. So a lot of times colloquially when we're talking about heat, we think of it as like something that's inside of something, but it's not really a thing in itself. It's thermal energy is the thing. Heat is the transfer of that, the movement of thermal energy from one thing to another. We can picture the process of heat here where we have a hot sink and a cold sink. And then when we bring them together, when we allow these molecules to bump up against those molecules, even through some sort of barrier here, eventually what's going to happen is they're going to reach thermal equilibrium. Eventually they'll both be at the same temperature and both sides will be moving relatively, the molecules on both sides will be moving at relatively the same speed. And that's due to the transfer of heat from the hot sink to the cold sink. Matter undergoing chemical reactions and physical changes can release or absorb heat. A change that releases heat is called an exothermic process. An example of that is a combustion reaction that occurs when using an acetylene torch. So anytime you have fire, that's an exothermic reaction. Lots of heat is coming off. But a change that absorbs heat is an endothermic process. This is like, for instance, when you have one of those cold packs you see in the medicine kits, first aid kits. Here we can see the acetylene torch in the instant cold pack. There's also the little heat warmers and stuff that you might see in the winter sometimes, and that's a chemical reaction that's occurring that's releasing heat, so that's an exothermic reaction. So, units of heat. Historically, energy was measured in units of calories, and a calorie is the amount of energy required to raise 1 gram of water 1 degree Celsius. And because the difference in temperature in degrees Celsius is the same as the difference in Kelvin, it could be called the amount of energy required to raise 1 gram of water by 1 degree Kelvin. Do be careful with that because it's only the differences in those temperatures that are equal to each other. It's not the actual absolute temperatures. This is a little confusing because we're used to seeing calories as far as food, but that's actually a different kind of calorie. It might be nice if they actually spelled it differently, but they didn't. Instead, they just put a capital C on it. And what that is actually 1,000 little c calories, or 1 kilocalorie. And if you're not sure what I'm talking about, this guy right here, that you'll see on the nutrition facts, has the number of calories in it, and you can see that that's written with a big C there. In most of our work, we're going to be using the SI unit, which is called a Joule. It is defined as the amount of energy used when a force of 1 Newton moves an object 1 meter. And it has a conversion from calories to joules, where 1 calorie is 4.184 joules. And you'll see that number popping up whenever we're working with water, the 4.184 joules number. So, heat capacity of a body of matter is the quantity of heat it absorbs or releases when it experiences a temperature degree change. So the temperature is either raised or lowered 1 degree Celsius. So here we can see that our heat capacity C is equal to the heat divided by the temperature change. So here's the important thing about this. The heat capacity is an extensive property. That means that if I have, say, a cup of hot water and an entire pot of hot water, even if they're at the same temperature and the change of temperature has been exactly the same, the pot of hot water is going to have a higher heat capacity because there's more of it. As you make the system larger and larger, the heat capacity will also get to be larger and larger and larger. Now, that's not very useful to us, right? We want a quantity that, regardless of the size of our system, we can apply it and we can know what the heat change is going to be, or calculate the temperature difference, for instance. So for that, we have the specific heat capacity. And what we've done here is we've taken the heat capacity and we divided it by the mass. Okay? So now we have a value that is per mass unit of our quantity. Okay? So even if the heat capacity rises because we have more and more mass, the amount of temperature change per unit of heat, or the amount of heat required per unit of temperature change, is not going to change gram per gram when you're using the specific heat capacity. This makes it an intensive quantity, and you'll see that we're going to be using this for the majority of our calculations. Here's an example of it. Due to its larger mass, a frying pan has a larger heat capacity than a small frying pan. Because they're made of the same material, both frying pans have the same specific heat. So one thing that we can do when we're using specific heats is have various ones for all of our different compounds that we're using. So we know that whenever we have a system that's just helium, it's going to have a specific heat of 5.193 joules per gram Celsius. A lot of our calculations are going to involve water, and you're going to see that number again, 4.184 joules per gram Celsius is its specific heat. Calculating heat. So the amount of heat that we're going to abbreviate with a Q entering or leaving a substance can be calculated by taking the specific heat capacity, multiplying it by the mass of the system, and then multiplying that by the change in temperature. And the change in temperature we're always going to calculate as the final temperature minus the initial temperature. So you can see that if the substance gains thermal energy, the final temperature is going to be higher than the initial temperature, then the value of Q is going to be positive. So when energy is going into the system, we get a positive heat. If a substance loses thermal energy, then the final temperature is going to be less than the initial temperature. Then the value of Q is negative. This is usually how I see this defined. However, if you guys do go on and see some other textbooks and some other disciplines besides chemistry, sometimes these are actually reversed. So it's always important to know what kind of definitions you're working under. But for all of our work, when a substance gains thermal energy, we're going to have a positive Q. And when that substance loses energy, we're going to have a negative Q. So a flask containing basically 800 grams of water is heated, and the temperature of the water increases from 21 degrees C to 85 degrees C. How much heat did the water absorb? So the first thing we need to know is our specific heat capacity. And that is a lookup thing, right? That would be like going back to this table and taking a look here and saying, oh, okay, water is 4.184 joules per gram Celsius. The next thing is multiplying it by its mass. And we were given that right in the problem, right? We were given water in terms of grams. It wasn't even a volume, so we don't have to mess with the density here to get the mass. We'll just plug that value in directly. Then we need to figure out what our delta T there. So it says from to. So the 85 degrees Celsius, is our final temperature. That's going to go first. And we're going to subtract from it the 21 degrees Celsius. When we plug all those values out, we get a value of 2.1 times 10 to the 5 joules, which is pretty big, and that's the way that you should expect your joule values to look. It's a pretty small value. That's why often it will be written out as actually kilojoules. You'll do a little conversion at the end here and divide this by 1,000. Let's double check our units again. Here we've got joules per gram times degrees Celsius. We multiply that by grams. That cancels this grams here. We multiply that by degrees C. That cancels that guy down there in that denominator. The only thing we're left with is a numerator of joules. So you can see an example of harnessing heat energy here. This is a process where they take a whole bunch of mirrors like out in the desert and they kind of focus it all on one point in order to heat that water up to a boil. And then when they do that, it produces steam that they force through a turbine. It's kind of like a giant magnifying glass that you may have used when you were a kid to say, like, set a leaf on fire or something cool like that.